Hello, today I would like to talk about solving nonlinear multivariate equations. So we're going to remember what we did with Newton-Raphson when we had one variable, univariate, and then we're going to look at a linear iterative method where we talked about Jacobi or Gauss-Seidel, and then we're going to transition to a multivariate nonlinear iterative method that's based on a multivariate Newton-Raphson, and that is where we find our Jacobian. We're going to look at a pretty easy example, the intersection of a circle and an ellipse, and then we're going to look at a more challenging deformable truss example. So remember your Newton-Raphson where you have a univariate function, and you need to be able to differentiate that function. And the basic idea is that the next point is the current point minus the evaluated function over the evaluated derivative. And that, remember, comes from everything comes from Taylor series, it seems, but a first order Taylor series expansion of the function of the next point is equal to the function of the current point plus a derivative of the current point times the step from the current point towards the next point. And what you do is you set the function at the next point to be 0, and that's how you solve for that. So that's the basic idea there. Gauss-Seidel, and actually I'm going to talk Jacobi here, that's an iterative method for solving a linear system where you don't have to invert the A. So if inversion is too much for you, you can solve it this way iteratively. And you might have an n by n A matrix, and then you'll have a B column, and then you'll have an X column, the thing you're looking for. And the idea behind Jacobi is that you iterate and you have some current idea of what your solution is, and you multiply it by a C matrix and subtract that from a D vector, and that gives you your next position to consider. If we look at an example, 3x3 example, it becomes clearer. So if you had a 3x3 AX equals B, and you sort of split the A into a diagonal part and an off-diagonal part. And then you think about taking that X and distributing it in there, and you let one of them be your current iterate, and the next one would be your next iterate. And then you basically invert, do a trivial invert there, and that's how you get the idea behind Jacobi. And that's your C, and that's your D. A little bit of a side note here is that you can see here why this works for a case where you're diagonally dominant in the A matrix. And if your matrix is not diagonally dominant, you could try to reshuffle the rows is one option. Another option is you could do a relaxation method where you let the next iterate be actually a linear combination of this one and this one. So anyway, so that's Jacobi, a little bit of a side note there. So when we hear the word multivariate, that simply means you're dealing with more than one variable, and you can take the variables, say x1 through xn, and put them together into a vector, call it x. And if you think about a function that operates on those n variables, a particular scalar function would be called a multivariate function. So f1 could be a scalar function of those n variables. If you take n of those multivariate functions and put those together, then you have a vector f of multivariate functions. And what we do is we think about iterating we may have an iteration at some step I, let's say. So the way I denote that is I put it in the superscript area that we're working on, iteration I. I put it in parens so it doesn't look like it's a superscript. And then we evaluate our functions at that particular xi, and this is how I denote it. I could have put the iteration on the x here maybe, but I've put them on the f. Hopefully it's clear in the context. Sometimes I just show it like that, not even showing the x, but anyway, so that's why I do it this way. And the idea is we're trying to iterate on this x. We're trying to change our x's so that we get those scalar functions to all vanish simultaneously. So vanishing means that the function goes to zero, all of the functions simultaneously. When that happens, that xi is said to be a solution. We're going to be dealing with nonlinear situations. So you actually may not have a solution. So you may have zero solutions, you might have one, you might have more. I'll show you a good example in a moment. You guys remember Taylor's series? Seems like it's ubiquitous. But what I'd like to do is take the first function, that scalar function of the multiple variables, the vector x, and I'd like to do a first order Taylor series expansion. And what that means is that the next function evaluated at xi plus 1 is going to be the scalar function evaluated at xi, and then I'm going to have the step between xi and xi plus 1, and I'm doing that for each of the n variables. So you have that step, but you also, with the Taylor series first order, you're going to have partial derivatives. You're going to take your first function and you're going to differentiate it with respect to x1, with respect to x2, with respect to xk here, say, and then finally with respect to xn. So this is the first function, and you're doing partials with respect to each of the variables, and you're multiplying it by the step that for the corresponding variable. It's pretty straightforward if you think about it, if you remember your multivariate calculus. So I do that for the first function, and then I repeat for the second function. I do exactly the same thing. Okay? And then there's a pattern. My goodness. So you just go down until you do all the way to the nth function, and you pretty much have it from a down at the micron level here. You have it all squared away, and what you could do is rewrite it in terms of a matrix form, and you could put all of the functions together, and you can put the partials together. So the first row is the first equation. The second row is the second equation. And then the last row is the nth equation. And if you look, thinking about the vector you've put together here, if you look, that's the first variable. So the first column of this matrix will be the with respect to's, the first variable, with respect to the second variable, and so forth, all the way to with respect to the n variable. Very nice. Very nice. So that is your Jacobian. It's a matrix. It's going to be n rows by n columns. Very beautiful, and it better be invertible. We're going to talk about invertible Jacobians today. So this is going to be your next step. So that's the function evaluated at the next iterate. That's the function evaluated at the current iterate. That's your Jacobian. And then here, this is the next iterate, I plus 1. And here is your current iterate, I. So we're looking towards a multivariate Newton-Raphson. And if you take the matrix form of the first order Taylor series, what I just showed you, let's back up. I just showed you that is the first order matrix. Let's put these together like that. First order matrix representation. And the idea is you want this to be 0, just like in the univariate situation. You want that to be 0. So set it to 0, and then you multiply through by J inverse, and then you solve for xi plus 1. And that is what you use. That's 12 equations 1217 in the book. This is what you use to iterate. Okay, I'm pretty excited to show you this example. It's two variables, x and y, and I'm going to be looking at two multivariate functions. The first one is x squared plus y squared minus 4, and the second one is 2x squared plus 6y squared minus 10. And if f1 is equal to 0, of course, that's a circle. And if f2 is equal to 0, of course, that's an ellipse. And I've drawn them over here, actually. And I've highlighted one of the solutions that we're going to be looking for. But you can clearly see here that there are 4 total solutions. Remember that a quote-unquote solution is an xy pair where both of the functions vanish simultaneously. And that happens there, 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 there. And I've written the Jacobian or the first order Taylor series expansion here. And I've put the f at iteration I, I've put that over on the left-hand side. So it makes it look really nice to show you really what the Jacobian does. The Jacobian relates changes in the iterate to changes in the function. And you can see the Jacobian very nicely in the 2x2 that the first row is related to what would be the first function. The second row is related to what would be the second function. The first column is with respect to x, and the first column is with respect to x, and the second column is with respect to y. Typically, the way I'm wired is I think of my Jacobians by way of column. So I'll take my multivariate functions and differentiate with respect to each variable. So if I think of f1 and f2, first of all, differentiated with respect to x. So I'm looking at, first of all, f1 with respect to x, so that would be 2x. And then if I pick up f2 with respect to x, that would be 4x. So that gives me my first column of the Jacobian. And then if I go back and do it with respect to y, I would have 2y. And then my f2 would be 12y. So very straightforward. Again, I'm wired, and I think in terms of columns because I'm a chematician, quite frankly. But that's what we do. So so that's f1 equals 0, it'd be the circle. f2 equals 0 is the ellipse, as I showed you. And one of the solutions is x is square root of 7/2, and y is the square root of 1/2. And those actually cycle through by way of signs to the other 3 solutions. And there's this theorem called Bezout's theorem that says there would be 4 solutions in the case of 2 intersecting conics in the plane. This is always true if you're thinking of complex points. And just as a side note here, think about my circle. I could make my circle bigger, bigger, bigger so that there would be no real solution to the situation. Here you see 4 real solutions. But if I made my circle bigger, 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 the solutions would actually become complex. But if you're only searching in the real domain, you would actually have no real solutions if I had a bigger circle. Kind of an important point. And the solution that I'm going to be looking for from the perspective of floating point would be about 1.87 and 0.707. And where I'm going to start, my first iterate is going to be 1.4 and 0.4. So I'm going to start there, and then hopefully I'll be driving towards that solution. Had I started in another quadrant, I would actually be driving towards that particular solution in that quadrant. So you're going to be looking for a solution that's nearby where you are. It's an important thing. Okay, I fired up my UF apps, and I'm going to show you some Mathematica stuff. And you don't have to use Mathematica, but I thought I'd show you a couple of different things there. In Mathematica, if you type something like I've done here, I've typed simply my two functions, and what you do to get something to quote-unquote run is you do a shift-enter. So I hold my shift key down and then I hit my enter. And what it's doing is it's defining F1 and F2, my two functions, and then I'm doing a contour plot of those two functions where they are vanishing each individually. And it's showing you the graphs, how I did the graph that I showed in my PowerPoint. But one thing with the Mathematica is when you see things in black, then those are things that are defined, and things that are in blue are things that are undefined, or here would be my variables. So just a side note there. So that was my first step that I did when I was preparing for this presentation. The second thing I did in Mathematica is I used the solve function. This analytically solves for the simultaneous XY answers to those two functions vanishing. And it'll give you the answers, and I assigned it to a variable called solve1. And you see the result. So it gave me 4 XY pairs. This is how it gives it. It gives it in terms of a Mathematica substitution. And the substitution will be, okay, X is, in my case, I want the fourth one. X is square root of 7 halves, and Y is the square root of 1 half. So that's why I take XY and I do the / dot solve for. So that's taking the XY and it's substituting that last solve, and it's giving me that pair 7 half square root and 1 half square root. And then I've defined my quote unquote end variable, end1, as n. The end function takes and changes it to a numerical answer. So I just wanted to kind of grab that, and that's what I put in my PowerPoint that I just showed you. So n means change that to a number, quite frankly. And then I'm going to start, as I said, I'm going to start at 1.4 and 0.4. And I just wanted to see if I could plot out some things, and I showed you a couple of things that I plotted. I add these epilogues where I add a green point, which is my start point, and then I added a red point, which is my end point. So I'm just kind of showing you some different things I was playing around with to do the presentation. And then I just did like a little test to show using the epilogue function that I could, yea, verily, plot between the start and the end point. So just having a little fun here with the Mathematica, just some preliminary things before I go and do my Newton-Raphson multivariate. So for that, here's what I did, is I put together an array or a vector f based on my f1 and f2. And I didn't put a semicolon there, so that should show me when I ran it. It does. It shows me my two functions. And it kind of reorders things. It put the -4 as the first term and the -10 as the first term in the second function. So those are my two functions, but again, it just kind of shuffles things around. And then I was trying to play around with, I wanted to be able to glue my my Jacobian together by way of columns, as I told you. So I looked at, okay, what if I took a derivative of that function with respect to x? That's a vector function, so that's both. And I wanted to say, what is the dimensions of that? So it's only 2. I want a 2 by 1. So then I said, well, I'm going to make it into a, I'm giving you guys a little bit extra here, but just kind of bear with me. But anyway, so I take that and I repeated it in terms of putting braces around it. So braces are arrays in Mathematica, and that shows up as a 1 by 2. I really want a 2 by 1. So that's, I do that, and then I transpose it, and then I check my dimensions then. And so I kind of have to play around with this every time. So 2 by 1 is what I want, and yeah, it's 2x and 4x. And then I did it again for my y, and then I can join them together by columns, and that's how I created my j. So I'm going to upload this. If you want to play around with it, it's up to you. But I'm just showing you what I did, and I'm showing my f, and I'm showing my Jacobian that I had in my PowerPoint just a moment ago. This Jacobian is analytical, so what I could do is I could substitute in any given instant my x and y values and calculate an actual numerical representation of Jacobian, and that's what I do. So I start. My start point is a 1.4 and 0.4, as I said, and I'm going to, over the course of my for loop, I'm going to be appending points to my points array, quite frankly, and so I'm starting at that start point, and so my points 1 at I is 1. My points 1 will be the start that I've already preloaded. So I do the same thing. I've already shown you this. I initialize my sort of search, and that's what I've done. And then the way it works in Mathematica, again, is I'm setting up these substitutions, and it looks like what my variable, and then I have a right arrow is going to be my cur 1. So cur is going to be whatever it is. I is 1, that's going to be my start. So I'm going to take that first point. So it's going to be 1.4, so I'm starting my first search for x. And 0.4 is going to be cur 2, that's going to be my y. And then I evaluate my Jacobian based on that. And I also evaluate my function, and then I print out my current position and my current function. Now, so all this is kind of precursor, and I could shorten this all up. But I'm debugging my print now, so I'm kind of evaluating my function, just like I've taught you before. I do some debug, and now I'm getting my next iterate. So my next iterate is going to be the cur minus the inverse of the Jacobian times my function. And these are vectors, so that's 2 by 2 in this case, and 2 by 1. And then whatever my next is, I append it to my points so that the next time up, points 2 will be the previous next. Okay, and I do that about 10 times. Well, I do it 10 times. I don't have a stop criteria kind of set up here, but when I run it, I start at 1.4 and 0.4, and it had a pretty big f error there, and I just iterate. And remember, it was about 1.87 and 0.707 for my solution. And you see, I kind of get it in 1, 2, 3, 4, 5, 6 steps, because my f is basically 0, 0, 10 to the minus 16th, 10 to the minus 16th. Again, I didn't show you how to do a stop criteria here based on the f's, but you can see I'm pretty much there on that iterate, and then I just kind of kept going because the for loop didn't break. Is what happened there. But you can see that I get to the 1.87. You can also see I went past it. I went past it on the first one. We'll see that in a second. Because I do a contour plot. I take the points and put those in the epilogue like I had kind of prepped before. And I do my points in a line in dark green. And then I do my start point, point 1, in green. Dark green is my line, and then I do a point for my start point in green, and then I do red. When I do points -1, that gets the last one. Red's going to be your final point. So see what that looks like. So that's what the contour plot looks like. I've exploded a little bit. So light green point, dark green line. So you see I shot past it, as I pointed out earlier, and then it comes back to the red. So very cool. And that's kind of what I wanted to show you for the very simple ellipse and circle example. Okay, I thought I would take a look at a pretty challenging problem, a linear problem that's challenging, but then we're going to even take it up a notch and go nonlinear with it in a moment. But first of all, take a look at the linear example here. It's a statically determinate truss, and the truss is made up of 3 struts or legs, and it's got a 1,000-pound load at the top node 1. There are 3 nodes. Node 2 is over here on the left. It's got a pin joint. It's pinned to ground there. And then node 3 is over here on a little bit of a skate. So it can take a vertical load, and it would actually skate left and right. The H2, V2, and V3, those are really internal loads. This is, quite frankly, not exactly a free body diagram because you've got things shown as being fixed. But if I were to take away those fixed constraints, then these H2, V2, and V3 would be internal loads, and the 1,000 pounds would be an external load. And then you would have the 3 struts. I've shown the 30 degrees. I've labeled that as theta 2 as it goes with the node 2. And then there's theta 3 that goes with node 3. So I've done that. In my notes, I had that as theta 1, but I didn't label it as such there. But let's go through the write-up that's shown in the book. There's a lot of positives here in this problem. So it says figure P1120 shows a static determinate truss. This type of structure can be described as a system of coupled linear algebraic equations by developing free body diagrams for the forces at each node. This doesn't do that, but I'm going to show you something in a minute towards that end. At the forces at each node. The sum of the forces in both horizontal and vertical directions must be 0 at each node because the system is at rest. Therefore, for node 1, it gives some equations. For node 2, it gives some equations. For node 3, it gives you some equations. So it goes node by node to give you those. And then it says where Fi, H is the external horizontal force applied to node I. So you got node I, 1, 2, 3. And then it starts to give you some conventions, and you have to pay attention to the conventions where a positive force is left to right. That would be for a horizontal one. And then it says where FIV is the external vertical force applied to node I, where a positive force is upward. So that would be from down to up, would be positive for a vertical force. Thus, in the problem, the 1,000 Newton, that should be pound, the 1,000 pound downward force on node 1 is F1V equals minus 1,000 because of the convention. And then it says to make all of the other FIVs and FIHs as 0, and they show up in the various equations here. Now, the internal F forces, it gives you a little bit more on that. Note that the directions of the internal forces and the actual directions are unknown. But what we want to do is we want to set up some consistency. Proper application of Newton's laws requires only consistent assumptions regarding direction. Solutions are negative if the directions are assumed incorrectly. Note in this problem, the forces in all members, those are the struts, are assumed to be in tension. So positive force in the struts or the legs means that's in tension and is sort of pulling the nodes together. See that in a minute. A negative solution, therefore, would be compression. Those are with respect to the struts. The H2, V2, and V3, those are the internal forces I spoke of earlier. Those are given conventions right here. So left to right for the horizontal, down to up for the vertical 2 and the vertical 3. When the external forces are substituted and the trigonometric functions are evaluated, this problem reduces to a set of 6 linear equations and 6 unknowns. And the F1, F2, F3 are your unknowns, coupled with the H2, V2, and V3. Then it says, solve for the forces and the reactions for this case. And it talks about an inverse. We'll let that go for now. And then it says to repeat it where you've swapped the direction here. But for today, I'm just going to use that downward force. The F1V is going to be minus 1,000 for my example. So if we were to do some theoretical cuts of each of the struts, then you start to see what they're talking about. So this is kind of in my mind what I see when they talk about the struts being in tension. So my F1 is in tension. I see it's being stretched. I see my F2 is stretched. I see my F3 strut is getting stretched. That is the convention. And when I do that, I have equal and opposite at each of these theoretical cuts. And now I'm set up for success with respect to figuring out what my node 1 is going to be from an equation perspective. So that really becomes my quote-unquote free body diagram that it refers to here. Free body force diagrams for the forces at each node. So that is my node 1, and I can kind of pick this apart and see where this comes from. So, for example, let's pick up F3. So F3 cosine 60 degrees. So this is a horizontal projection. So there's my F3, and if I think about a horizontal projection, that's going to be cosine of theta 3. So that's F3 cosine of theta 3. It's going to the right, that projection, so it gets a plus. The F1, its projection is going to be cosine theta 2. That's going to the left, so that's why it gets a minus. So I'm doing a little bit more here in case you haven't had statics, but to help you support that. And then the F1H, they've said that all of these, other than the F1V, all of these are going to be 0, the external loads. So now let's go to take a look at our vertical for the first node. So from a vertical perspective, I do have that F1V, and again, yeah, that is going down, but we've already taken care of that by way of assigning it the value of minus 1,000. So that's good with the plus, because we're thinking of that in the convention of being up, being the external loads being positive. Now, the convention on the strut forces, each one projected into a vertical direction is going to be in a negative direction, and the projection would be a sine projection for each one because I've got the thetas marked over in that way. So they're going to be sine projections to get the vertical component of each particular force, and they're going to be negative because they're going down by way of convention. So that's how the first node looks. Let's go take a look at the second node. So for node 2, again, I've got my theoreticals, and that's how, with the second strut getting stretched, that's what it's going to look like over here. So if I kind of ignore that this is fixed for a moment, I have H2, V2, and then I have F1 and F2 acting at the second node. So it would be a free body diagram of the second node. And if I focus on maybe a cosine projection or a horizontal projection here, I've got cosine 30 for my F1, and it's going to the right, so it gets a plus. My F2 needs no projection. It's going straight to the right, so that's a plus. And then I have my H2 also. All three are going to the right, so they're all plus on the horizontal for node 2. And then node to vertical, I'm going to look at that. So again, everything is projecting up. I've assumed that's going to be up. Based on this assumed direction here, its projection is going to be a sine of 30, and it's going up also. So that takes care of that one. And then the last one, again, I'm cutting, and it's equal and opposite how it works here when you make a theoretical cut. So I've got my F2 going to the left. So that's why it's minus F2 in the horizontal there. And then for F3, it's getting a cosine 60 projection going to the left. So that's a minus. And the externals have been killed. So that's all I have there for horizontal. And then my vertical internal load, the V3 is going up. So I've got that as a plus. And the F2 has no projection vertically, but the F3 is going to have a sine 60 projection, and it's in the positive direction. So I've just walked through every free body diagram and set up two equations for each node. And it looks like I have 6 equations because I have 3 nodes, two equations at each node. So I have 6 equations. I have 6 unknowns. I've got the 3 forces, F1, F2, F3. I've got the 3 reactions, internal reactions at H2, V2, V3. And the only external load that we've applied in the example is 1,000 pounds going down. So that's the minus 1,000 F1V there. So then I implemented it again in Mathematica, and you can see clearly that I've got my Fy is the minus 1,000. That's going on to the second equation. So these 3 nodes, I have 2 equations per node, so the 6 equations are in the same order that I just talked about. And remember, in Mathematica, black means it's been defined, and blue means that's still a variable or an undefined thing. And I've actually gone through and set up my theta 2. I should call it T2. The R means it's in radians because I've configured it in radians there with the 30 times pi over 180. And the reason I do that is so that I can set up some substitution. So my C2 is a notation I use for the cosine of theta 2. My C2 is going to be substituted as cosine of T2R. So that's all known. So the subs 1 takes care of all my trigonometric substitutions. So I take these equations and I set them up and set them equal to 0 so that they simultaneously vanish, those 6 functions, and I do my substitution for the trig stuff. So those are my linear equations, and I use that solve again. I solve for my 6 unknowns, and solve 1 is going to give me one answer. It's linear. So I'm going to get one answer, and the solve is analytical, so it gives you back things having perfect square roots here of 3, for example. And then I do the n function again to show this percent means the previous answer. Whenever you see percent, that's the previous answer, numerical, and that's what it does. So I wanted to kind of show you that. And this is a baseline. I think this is actually a homework problem for you guys who are going to do whatever you want to do in MATLAB, whatever you're going to do in MATLAB to sort of replicate this, but I see this as sort of the answer to the first part. Okay, having done that, now let's take a look and appreciate what we have here and see if we can learn and understand. So I've got that 1,000 pounds pushing down right here on my truss, if you will. What's the answer telling me? Well, it's telling me that the F1 strut has a negative force. It's in compression because negative is compression. F3 also in compression. F3 in compression. So if I push down here, yeah, it's gonna compress that. It's gonna compress that. That's on a little bit of a skate. So it's going to pull on F2. It's going to give you a plus answer on F2. Correct, correct, correct. And I tell you, it's so easy to be off by a sign. And it's also so easy to catch it by just using some common sense. So right, right, right. And then I take a look at the H2. I've only got this 1,000 pound force pushing down. And if I think about it, there's really would be no reason to have a horizontal load. I only need to support that 1,000 pounds, and the V2 and the V3 will do that. The H2 should be 0. Makes sense. And then if I look at it, the V2 and the V3, hey, guess what? They are both positive. Yeah, they're going to be positive to support that 1,000 pounds. That 1,000 pounds is in the middle. It's closer to the third one. So that's why this V3 is a little bit higher than the V2, but they're both positive because that 1,000 is in the middle. It's in between. Had that 1,000 been over here, then it would cause that V2 to change signs. But anyway, it always makes sense to kind of look at it from that perspective, and you can catch mistakes. So it needs to be in agreement with what you kind of feel, and you gain a sense of intuition when you start doing stuff like that. So in summarizing the linear case, remember that my unknowns, my 6 unknowns, are F1, F2, F3, my strut forces, and then my H2, V2, V3, those horizontal and vertical reactions at nodes 2 and 3. Let's make it deformable. So we're going to replace each strut or leg with a spring. We're going to put some stiffness. We're going to assign a stiffness. It's the same stiffness throughout for each leg. And we're going to use Hooke's law and say that the force in each leg, like force in leg 1, F1, is going to be equal to K times the difference L1 minus L01. And similarly for the strut 2 and strut 3. So the lengths L1, L2, and L3, they change. And the angles change too. The theta 2, theta 3, they will also change. The L sub naughts, 1, 2, 3, those are free lengths or unloaded lengths, and I'm going to assign some values for them. I'm going to say, okay, my L naught 2 is going to be 12 inches. And then what I'm going to do is I'm going to use the 30, 60, 90 as the unloaded configuration. So using a 30, 60, 90 triangle, I can easily get my free lengths for the other 2 struts or legs. So I can get L naught 3, for example, is 6 inches from just that. So I'm set up now for success. So now the unknowns are L1, L2, and L3, because K is known. L naught 1, L naught 2, L naught 3, those are known. And so I have expressions for the forces. I have expressions for F1, F2, F3. So I'm not going to claim that they're unknowns. I'm going to claim that L1, L2, L3 are unknowns. I'm going to leave, those are lengths in inches, and I'm going to leave the H2, V2, and V3 as unknowns. And then in order to get my C2 and C3, I'm going to use a cosine law based on L1, L2, and L3 to get the cosine of theta 2 and the cosine of theta 3. And then I can use simple trig identity based on cosine to get sine of 2 and sine of 3. So everything in a layered way is dependent on these 6 unknowns. It's going to be highly nonlinear. If you're worried about the cosine law for theta 2, well, you have your triangle, of course, and we have theta 2 as an included angle. So the cosine law for that theta 2 is going to be the opposite length, L3 squared, is equal to the 2 adjacent lengths, L1 squared plus L2 squared. And then you're going to subtract off 2 times the product of the 2 adjacent lengths, and that's going to be times the cosine of theta 2. Easily rearrange for a cosine of theta 2, and you're going to have cosine of theta 2 in terms of the 3 lengths. Once you have that, you also have in a next layer, you would have the sine of theta 2 related to the square root of 1 minus cosine of theta 2 squared, and we're going to take plus the radical on that without a loss of generality. Okay, let's take a look at the Mathematica stuff. So I finished off with the linear, and I have my linear answer so that I can sort of compare when we go look at our nonlinear situation. And basically take in those same 6 equations, and I've defined some unloaded lengths, as I showed you, for the three legs or struts, and I've actually printed out a number just so I can get an idea of what the square root of 3 times the 6 inches is. So I have that. I'm going to do an example of K, stiffness being 5,000 pound force per inch. I've got a little function in Mathematica I call it cosine law, and it's just returning the functions based on what 3 lengths I send to it. So that's returning the cosine, and I use that for C2, and I also use it for C3, changing the lengths as necessary. And then I get my sine 2 and sine 3 squared away. So I've got my substitutions in terms of the L's, and now I've added to that my substitutions for forces, as you can see, and then I've got my 6 functions. Each one of these now is multivariate. E1x is multivariate all the way down to E3y. Those are my multivariate functions, 6 of them, and I'm doing my subs here. I'm doing my trigonometric subs. I'm doing my Hooke's law subs. So I've got my 6 nonlinear multivariate functions in terms of those 6 unknowns, and the unknowns are L1, L2, L3, and H2, V2, and V3. Those are my unknowns. And then here I print it out. See, I've got all semicolons except for that. Semicolons. So the first thing that print out should be my functions, and they should be pretty rough looking. So there's that 6 times the square root of 3. So here's what the functions look like. I'll zoom in maybe a little bit more. So that's what the functions look like, highly nonlinear depending on those 6 variables. And what do we have after that? So the variables, I just check to make sure, make sure when you do the variable function, it's given you the variables, the 6 that we have. It's different order, that's okay. And then I build the Jacobian. I start with a empty 2-dimensional matrix. That's how you do it in Mathematica. And then I go through the 6 columns, and as I told you, I think in terms of columns. So I'm taking it one variable at a time. I'm taking all of the f's, all 6 f's, and I do a derivative of those one variable at a time, and I just glue the columns together. And the dimensions of J should be 6 by 6. Yes, it is. And the J, and then I do a matrix form of J, so it pretties it up. It gives you a matrix look. So you can see there's some pretty gnarly stuff. So that's the first column. First column, pretty gnarly. Second column, gnarly. Third column, gnarly. And then the 4th, 5th, and 6th columns, look how simple they are. And that makes sense because if I go and look at the functions, and remember the order is L1, L2, L3. So those are the first 3 gnarly ones. And then H2, V2, and V3. H2 only shows up in H2 shows up where there it is. So it only shows up there in the 3rd function, and then V2 shows up in the 4th function. V3 shows up in the last one. So that's why in the Jacobian there's that 3rd one. That's the H2. Here's the V2, and here's the V3. So that's why those last ones are sort of trivial. So I have my J squared away. It's analytical. So now I'm going to start off my points, just like I did with the ellipse circle example. I've got 6 dimensions now, but I'm going to start at the unloaded configuration. So my 3 L's are going to be my L01, my L02, my L03, and I'm going to start out with 0 loads on the H2, V2, and V3. So that's my starting point, if you will. And I'm going to, just like I did for the ellipse and the circle, I'm going to let that be my start, and I'm going to only go 10 times here, okay? But it's really just a cut and paste of my previous one, quite frankly. I had to do a little finagling here so I could get my substitutions squared away. So this map thread is a function where it takes each of my vars. What's my vars? My vars. Here's my vars right there. So it's taking those vars and it's setting them equal to whatever's in that curve point. So these would be actual positions that start with, the 12 here, the 10 point whatever here, the 12 and the 6 and the 0, 0, 0. So that's going to be the substitutions for S curve. And then I use the substitutions in the Jacobian and also in the function. So same thing. And then I'm going to print out my curve point. I'm going to print out the current functions. That's my current iterate, current functions. And then in the homework, I said, hey, I want to know what the forces are. So I print those out, just like that, in terms of the expressions for force. And I also kind of wanted to print out how the current leg lengths are with respect to the unloadeds. So those would be maybe deltas. So I'm doing my debug, and then I go in and do my Newton-Raphson. And the Newton-Raphson is next equals curve minus the inverse of J. And I'm doing an N on that so that I'm not dealing with unwieldy radicals that keep kind of going back through in different loops. So I do a numerical right away of the product of the inverse of the Jacobian times FF curve, the current function. And then I take that next and put it on points, append it to points, so that next time through, the curve is going to pick up the last one that you appended. And then I print out the answer in a nice way here so that I can compare with the linear. So let's see what we get. So I don't know, we went about 10 times. So again, we start at that unloaded L2 of 12. I know that. And my L3 is 6, and then I have 6 times the square root of 3. So that's what I start out with. And then when I do the functions, it should be all zeros, but I've got that big offset there. And I've got no forces because I'm unloaded. So that's that very first start point. And then I start doing the multivariate Newton-Raphson. And the first time through, I get pretty close. I'm jumping up in force quite a bit. I've got, a tenth of an inch there in compression, 2/10 of an inch almost in compression. I'm stretching a tenth of an inch there, L2. So it's trending sort of the right way. And then I'm going to go take a look, see where it ends up. So this is where we end up. If you notice, the functions at the end are like 10 to the minus 12, 10 to the minus 13, 12. These are all very close to 0. I could probably keep iterating on this. I didn't discuss a stop criterion for you on this. But anyway, so I could have probably kept iterating. But we can take a look, see how it kind of looks right now. So on the last sort of loop, we had our current L1 at about 10.82. We had our current L2 at 12.09, and our current L3 was at 5.8. So remember, this started at 6. This started at 12. So this one's compressed. This one has stretched a little bit, and I can see here because I've got my delta L's. I can see here right away. So that L3 has compressed. L2 has stretched. That's what we know would be right. And then L1 is compressed a little bit. And if I look at the forces, how they're kind of configured, this is fairly stiff at 5,000 pound force per inch. So the forces, see, forces at, F2 is 463 for the deformable, and it was at 433 for the linear, infinitely stiff example. And for the deformable, I'm at minus 528 for F1, and I was at minus 500 for the infinitely stiff. So you can kind of see what's happened here. The compression looks like compressive wise, we're getting a little bit more compression, and even tensile wise, we're getting a little bit more on the force. And we could probably go through this another few times. But this H2 still about 0, which I think it will remain 0. 254, so a little bit more on the vertical there. The only thing that went down here, interestingly, is the V3 went down a little bit, but looked like everything else went up, at least in magnitude. But anyway, so that's how you do the nonlinear deformable truss example. Okay, wow, that was a lot, and hopefully you enjoyed some of it. We kind of reviewed some univariate stuff from Newton-Raphson, some relatively easy compared to what we looked at just a moment ago. We looked at some multivariate linear iterative methods, and then we jumped into the multivariate nonlinear iterative, where we looked at a Jacobian and we looked at Newton-Raphson, what that looks like. We did a circle and ellipse problem that was pretty nice and pretty straightforward. Kind of gave us a launch into the very sophisticated deformable truss problem, where it was 6 dimensions, highly nonlinear in 3 of the variables. So anyway, so hopefully you enjoyed it. Looking forward to some discussion.